In this video, we will talk about Riemann problem. It is a very famous problem in finite volume method. When we study finite difference method, this Riemann problem actually does not appear. And if you have studied finite difference method course, probably you never heard of this Riemann problem. The reason is the Riemann problem is a discontinuous initial condition in PDE, and we will talk about that later on. So these are the contents of today's video. So what is the motivation of studying Riemann problem? As in previous video, I talked about the discontinuous solution. For example, if there is some kind of explosion, and that explosion actually results into the discontinuous wave or a discontinuous solution. And to study those discontinuous solution, we need some structure in mathematics so that we can learn from that discontinuity. So that's why the Riemann actually constructed that problem. It is similar to the Cauchy problem that we have in partial differential equation. Cauchy problem is when we have initial condition, we have something at t is equal to 0 for in PDEs. So this was about the motivation. We study the discontinuous solution, and Riemann problem. I'll talk about that now. So how we formulate Riemann problem? We have a conservation. For example, we have a one-dimensional hyperbolic and 1D hyperbolic conservation law, which is written like this: partial u by partial t plus partial by partial x f of u. This is the 1D hyperbolic conservation law. It is hyperbolic since we say that the eigenvalues of the coefficient matrix are real, and conservation since this quantity, and we will talk about this quantity, this flux, actually this is called a flux. This flux of energy, for example, flux of momentum, so on, this flux actually remains same even though you apply numerical method. That's why it is called conservation law. And what is difference? What is the main thing in Riemann problem? The main thing is when we write initial condition, the initial condition is written like this: when t is equal to 0, then we have u left if x is less than 0, and on if x is greater than 0, then we have UR stands for right. How you visualize that? For example, you have x-axis, and on the y-axis we have solution. This is t is equal x is equal t is equal to 0, x is equal to 0, and on the left we have u left, something like this, and on the right we have, for it can happen that u right can be 0 or it can be like this. So if it is like that, then we have u right, and there is a discontinuity over here. Here we have nothing, we have maybe one value. For example, we have ux0 initial condition look like this. It is 1 if x is less than 0, and it is 0 if x is greater than 0. When we have 1D hyperbolic conservation law and the initial condition look like this, which has a discontinuity, then such problem is called Riemann problem. Okay. So there are this was the formulation. We will solve it in future. And what kind of wave types can appear when we solve such a problem? When we solve such problem, there are three kind of wave type can appear. The first one is shock waves. Then there are different kind of discontinuities. One is called rarefaction waves. And then we have, for example, contact discontinuity. So such kind of waves will appear. For example, if we have a shock tube problem, maybe we'll talk about that in future. This is just an introduction of the Riemann problem. We are not solving it. We are not solving this problem in detail. We'll do that in future. Shock tube problem, when we have, for example, this U as a density or some pressure or something like that, then that in shock tube problem, we have all these three discontinuities in shock tube problem. One thing you should remember that in fluid mechanics, generally, the people who are working in boundary layer flow or something relevant to that research area, U is generally in fluid mechanics, it is velocity. But here it is not a velocity. It can be, U can be energy, you can be momentum, you can be, for example, velocity as well. It's okay to have a velocity. So generally, you can be anything. So it can be density, it can be pressure, it can be velocity. Okay. So what is the importance? We reached over here. What is the importance? The importance is in numerical method, whenever we construct a new numerical method, in finite volume method, we apply that numerical method to the Riemann problem to see how good or accurate the numerical method is. For example, there is one famous scheme in finite volume method which is called Godunov's method. Okay, and also which is actually Riemann problem. It is generalization of Riemann problem. So analytical insight, we can have analytical insight. We can see how the solution look like, how the numerical method those we have applied look like. So we can have some kind of interaction of shocks and rarefaction, so on. So this was all about the importance of that. Now I will show you a very short animation so that you can visualize that. You can see that this is the, let me just stop it. Here we have at 1, x less than 0, there is condition 1, and on the right hand side we have a condition 0. So this is actually the Riemann problem. It looks different than Riemann problem, but it is a Riemann problem. The initial condition in this case was t is equal, x is less than 0, it was 1, and x greater than 0, it was 0. So this was all about the Riemann problem. Thank you for watching.